Looking at the acronym ARIO, the A stands for the type of atom that carries a charge. Let's look at it in context to compare the acidity of two compounds below. For instance, we have butane, we have propanol. Now these two, let's assume that they're acids, so they're gonna donate these protons. When we look at the type of atom that is going to be holding the negative charge once that proton is lost, we draw them and then we analyze that stability. As you know from our previous discussions, oxygen is much more likely to carry a negative charge, is more stable when carrying a negative charge than carbon. So what that means is that this oxygen carrying that negative charge will provide for a more stable base than the carbon carrying that negative charge. Therefore, this will be more stable, this will be more acidic. Here we can determine whether an oxygen or a carbon will better stabilize a negative charge. Less versus more stable, we already discussed that. When moving down a column, and we're talking about the periodic table here, size is going to be a very important factor. So for instance, if I'm comparing oxygen to sulfur, which is right underneath it in the periodic table, then sulfur will be more stabilizing than oxygen. The larger the atom, the more stable a negative charge will be. It has more volume to spread. For atoms in the same period, electronegativity is the most important factor. Since carbon and oxygen are in the same period, they are similar sizes. In this case, the more electronegative atom will better stabilize the negative charge, in other words, oxygen. And the conclusion of that analysis is that propanol is more acidic than butane. Let's look at the letter R in ARIO. R stands for resonance, and as we know, resonance stabilizes the negative charge or a lone pair by spreading it across multiple atoms. Comparing the acidity of the two compounds below, we can start looking at a pattern, right? We can start looking at how resonance is going to affect the acidity of any given system. Now, here we have ethanol. Oxygen will have a negative charge, more stable than carbon, definitely. Here we have acetic acid. This proton gets lost. This oxygen also will carry the negative charge. However, here you have this double bond, you have lone pairs, so you can most certainly have some resonance there. So you will have resonance structures that will allow for that negative charge to spread throughout this entire volume. In the case of ethanol, the oxygen will be the only one that carries a negative charge, so it's a localized charge. As you can see here, we have the charge being more localized, more delocalized, more stable. As a consequence, acetic acid is much more acidic than ethanol. Looking at that letter I in ARIO, that will be for inductive effects. Inductive effects can also stabilize a formal negative charge by spreading it out, similar to resonance. How are inductive effects different from resonance? That's a very good question. Electron withdrawing groups or atoms will inductively withdraw electron density from their surroundings, thus stabilizing the negative charge. So for instance here we have acetic acid and trichloroacetic acid. If you look at the left side of the molecule, you have a carbon atom with 3 protons, 3 hydrogen atoms, and then here you have 3 chlorine atoms, 3 highly electronegative atoms. And what will happen is that this proton gets donated, right, because we're assuming that it behaves as an acid. You get a negative charge. Now the negative charge gets spread out not just in this area due to resonance, but also this area due to inductive effects. So it makes for a much more stable system. As you can see, the pK values will reflect that reality. No chlorine atoms, 1, 2, and 3 chlorine atoms, you see those pK values drop quite dramatically. Doesn't look like a lot because it's a logarithmic scale, but keep in mind that a change of even 1 unit, that means a factor of 10. So here you actually drop 4 units, that's a factor of 10 to the 4. Last in our list of initials, the letter O stands for the type of orbital, which can also affect the stability of a formal negative charge. The closer electrons are held to the nucleus, the more stable they are. The shorter the atomic orbital, the closer to the nucleus. In other words, when you have something that is a little bit shorter, you're going to get closer to the nucleus, that attraction becomes stronger, but as you move away from that nucleus, then the attraction becomes smaller. Consider the relative stability of the protons in this molecule, the red one versus the blue one. To predict which proton is more acidic, we must first draw the two possible conjugated bases. So we're assuming that a proton gets lost here, and we're also assuming that a proton gets lost here in two separate scenarios. That leaves us to carbanion species, so carbon with a negative charge, and we need to figure out whether the structure on the left or the structure on the right is more stable. The bigger or the larger the s character in the orbital, the more stable the negative charge. And as you know, when you go from single sp3, s is just 25%, sp2, that'll be 1/3, so 33%, sp, that's 50% s character. So you went from 33% s character to 50% s character. This will make for a more stable compound. Comparing apples to apples now, single, double versus triple bond, you can see the pK values, they drop quite significantly, 25 units between the single and the triple bond. So as you can imagine, the strength of the acid is very strongly related to the type of orbital that we have available. When assessing the acidity of protons, we generally use REO as the order of importance, so the A goes first and the R, etc. is not random. The type of atom that carries the charge, the resonance, the inductive effect, and then the type of orbital. Keep in mind though, this is a guide, so it will help most cases, but there are exceptions. There are cases in which this isn't accurately followed, so you have to be able to analyze everything on a case-by-case basis. Let's look at an example here. Ethanol is more acidic than propylene. Therefore, the conjugated base of ethanol must be more stable. Type of atom is consistent with this fact, oxygen versus carbon. But if you look at propylene, the conjugated base, it is actually resonance stabilized, which will give you a little bit of pause. Unless we know that the REO, ARIO, they're followed in order of priority. So A goes before R, therefore this is actually accurate. As I mentioned before, this is just a guideline. It works a lot of the time, doesn't work 100%, sometimes fails. Here, for instance, we know that the equilibrium lies to the right because we know the pKa values. Right? Always knowing pKa values will give you much better chance of accurately predicting direction and acidity than the REO. If we had judged the conjugated base stability, we would have concluded the negative charge on nitrogen is more stable than carbon and predicted the equilibrium to lie to the left. That would have been a fair observation. However, it is actually incorrect. So what I want you to take away from this is that for some acids, we simply need to know the pK values because there are exceptions to the REO priority rule. This is going to become a lot easier and more clear as you practice. So my advice at this point is to start practicing and start looking at these molecules, start looking at pK values, start practicing that REO so that you can get a good sense of what are stronger and weaker species.